Hey, my name's Casey, and if you want to see me walk through more LeetCode solutions, you can subscribe. So I'm going to go through LeetCode 1268, search suggestion system. So let's just look at the example that they give us. They give us a list of products and a search term. And all they want us to do is, let's just hypothetically say that this product is sorted, or that that list of strings is sorted. It's not, but let's just hypothetically say that. All they want is, let's just take this first letter M. They want us to return the first three words that have the prefix M in our hypothetically sorted list of strings. And then we would do the same thing for MO, then MOU, and that's how they're doing this. So for M, you would get these first three words, then this would be MO, MOU, and then MOUS, MOUSE. Okay, so that's what they want. Now, how do we do it? There's a few approaches. So the first approach is, you could do brute force, but we're not doing that. Then the second, there's another approach where we can use a try data structure, and the try data structure is the optimal approach, but I'm not a fan because under time pressure, it's a lot of code to write to build the try with the products and then look through the try with some backtracking to find the prefix and the next few words after the prefix. It's not fun to write. It's like if you mess up, it's very easy to mess up somewhere because of how much code there is. So under time pressure, I don't recommend doing that approach. But if you're a try master, by all means, go for it. So the third approach, which I'm going to be coding out and showing you how to do, is we could just sort the products, and then we can just do a binary search for the first word in the products list that our prefix is less than or equal to. And that is just called a lower bound binary search, or binary search lower bound. And you could do an upper bound too, but we're doing a lower bound binary search on our sorted products list for that first prefix. For the first word that is less than the first word that our prefix is less than or equal to. And you know what? Let me just type a quick examples to make that super clear. So let's just say we have cat, cats. We'll just go with abracadabra. I don't know. I'm just making up words here. And then eel and zebra. Okay. And you know what? For the heck of it, I'm gonna throw in a duplicate in there. I don't think there are duplicates in the products. I'm pretty sure there's not. But even if there are, it doesn't matter. So let's just say that the prefix, and this is our list of products, okay? And I didn't put commas, but whatever. Our prefix, let's just say the prefix that we're looking for is cat. Well, I know we could do the C, the A, but let's just do the whole thing. Let's just say we were looking for cat. The lower bound index would be this guy right here. It's the first word in this sorted list of strings that our prefix is less than or equal to. Okay, and if this, let's just pretend that cat and cats was not here. So let's just say we only had cats. Then we're gonna return index 1 here. Because cat is less than cats in terms of alphabetical or lexicographically order. It's the same thing. Okay, so let's actually code this out. So first, we're gonna sort the products list. So arrays.sort products, boom, sorted. Then let's go ahead and just type out that lower bound function so you can see it. So private int lower bound, and I'm returning an int because again, this is returning the index of the first thing that our prefix is less than or equal to. So we're gonna pass in, just go ahead and copy and paste this. The same exact thing. Okay. So it takes in our products, and instead of search word, I'm going to pass in prefix because this is actually a prefix of our search word. So if they type in, because remember, if they give us mouse, this could be the letter M, and then the next time we call us, it'll be MO, then MOU. Okay. Let's keep going. Let's type out this lower bound function. This is just a binary search with a little bit of a little tweak. So int low equals 0, int high equals products.length. And you want to say, well, low less than high. We'll calculate the mid equals low plus high minus low. And sometimes whatever, keep going. Divided by 2. And so now we have our low, high, midpoint. And what we want to say here is if our prefix, and we have to use the compare to function because it's a string and not an integer. So prefix compare to products at the midpoint, it's less than or equal to 0. And this is the magic right here. This is what's accomplishing finding the first word in our products list that our prefix is less than or equal to. Okay, so what we want to say here is if it's less than or equal, then high equals the mid, and high here is exclusive, not inclusive. So it's exclusive because we set it to the length of the products. Okay, so we're setting high equal to mid here because we already checked mid, so this is exclusive. Okay, else low equals mid plus 1. Okay. So yeah, and in the case where, let's just say let's just go with cats again. Let's just say that we were looking for, and I'll just add in another word for, because why not? Oh shoot. What the cat? Okay. Let's just say the prefix that we're looking for is dog. Dog is not less than or equal to anything in this products list. It's not less, D is not less than C, right? D is greater than all of these. So in this case, what would end up happening is high is set to the product's length, right? Eventually low is going to equal high. So eventually low will actually equal the length of our products. And actually, I forgot to return something. So low will so what we'll end up returning is just the length of our products. And that just signifies that our prefix is, or that our prefix doesn't exist. Or there isn't, no, sorry, not that it doesn't exist. That there's no string in products that our prefix is less than or equal to. Okay. So now that that's taken care of, oh, and I'll just add one more thing about this. We could return low or high here. It doesn't matter because the way that we get out of this is if low equals high. So good. Hope that's clear. And if we want it, I'm just going to throw in a little bit of information here. If we wanted to look for the upper bound, where like the first word in our products where our prefix is greater or equal to, all we would have to do is delete that little equal sign there. And that now turns into an upper bound, but we're doing lower bound here. And I don't want to get too into this because there's plenty of videos that explain how to do a lower bound binary search and an upper bound binary search. Like I'll link one in the description, the one that helped me out. And you should definitely practice writing a binary search on your own and like a lower bound binary search and upper bound binary search. And do like an upper bound binary search exclusive and an upper bound binary search inclusive. I'm just giving you tips here. And just to prove a point, like I did it. Like that's how I got good at writing binary search. Just write a bunch of versions of it. Okay. So let's keep going. So now we've got our lower bound function to find the index that our prefix is less than or equal to something in the product list. So then now we want to actually simulate that whole, like, so if they give us mouse, we want to be able to simulate M, MO, MOU, where we're searching for these prefixes, right? Let's go ahead and create this prefix. And we want to go through our search word, .toChar, and we're going to add a character to our prefix. So now that's simulating the M, the MO, MOU. Okay. And so on. And we actually need to return something here, right? Like that's the whole point of this method. So let me add that really quick. So we're just going to call this all suggested products. New, let's make it an array list. Did I just put 3 R's? I did. All right, so all suggested products array list. Okay, and then we also need, so this is a list of lists, right? So the thing that we're actually going to return, well, we're returning this. So let me just write that out really quick. So we're returning all suggested products, but we need to have like an inner list or whatever you want to call it. of just we just need the 3 suggested products that go with this prefix. That's all this is. Okay, so array list, or sorry, this should just be list of string. Okay, so we want the first 3 words in this products list that match this prefix, and we're going to put in these suggested products, and eventually we're going to add the suggested products to all suggested products, and then we just return that. So we're almost done. We just need to actually loop through, or we need to actually call our lower bound function. So this is the index that we want to start at. We're going to pass in the prefix. Okay, so this is just the index this is the first index where my prefix is less than or equal to. Remember, it's not necessarily equal, so this index that gets returned, it might not actually have the prefix at all, which we have to check for and account for. But anyway, let's just write the loop. So this is the index we want to start at. I is less than start plus 3 because we want 3 products, and we want to make sure we don't go out of bounds. So let's just make sure we're less than the product's length. Plus I. And then again, so this start index might not have our prefix, so we have to account for that. So what am I checking here? If products dot or products I whatever starts with our prefix, if it doesn't start it, we'll just break out. And now that we know that it does have the prefix, we can go and add that to our suggested products. Oh, wait, not the prefix. What am I doing? Products I. Okay. And I think this is done. I think we're good. We can just check if this works, try to make any typos, and I didn't. Cool. And okay, so this is the solution, but there's some small optimizations we can make to this, and I do want to go over those. So let me go back to the description because I'm used to looking at that. Get rid of this. Okay, so notice when we're calling lower bound, we're always passing in we're always doing our binary search on the entire products, on all the products, right? But once we've found our prefix, like once we find the first word that say starts with an M or a C, whatever. Let's say our prefix is, let's just go with mouse because that's the example. Let's say we pass in M, right? For the first call to lower bound, M will be our prefix. Well, now we just want to start when we pass an MOU on the next iteration, we want to start at the words that started with M. And I think that makes sense because there's no reason to start looking at the words that start with, say, A, B, C, D, right? Or any letter that's A through, what was it? I don't know my ABCs, but A, B, C, D, E, F, G. We don't need to look at those anymore. We don't need to binary search on that part of the products list. So we can just go ahead and pass in where we left off last time. So let me think of so we want to move this out instead of let's move that start variable out here. So so at the beginning, we're always going to start at 0, right? We want to look at the entire products list from the very beginning. And we can go ahead and pass in start here. And let's go ahead and do that. We'll pass in start here. And now we'll set low equal to start. So now that we've basically cut down the range of where we're binary searching because we know we don't have to look at anything before that. Okay, so this should just work. Okay, cool. Still works. And we could do the same thing for the end of, we could like basically limit, so we limited our range from the start. Now we could limit our range from the end. And the way we do that, I actually have to think about it for a second. let's see, we start with, oh, okay, yeah. So int end. So at first we're gonna look at the entire product's length, or we're gonna binary search on the entire products, right? So that's why end starts at products.length, and the reason is because eventually I'm gonna pass an end to my lower bound, and we're gonna set high equal to end, so that we can limit our binary search of where from the start to end. So where do we want to actually update this? And we actually want to do it here. And I'll explain why in a second. Let me just type it. I hate my computer on the tabbing sometimes. Okay. Or maybe it's just LeetCode. Okay. Not int end. End equals I. Okay. So we want to update end here because this is the first word. So this is where we're starting at, right? We start at this lower bound, we start looping from here, and as soon as we encounter a product that doesn't contain our prefix, well then we know we don't need to look past that anymore. There's no reason to say, I guess I can go just type out a really quick thing. Okay, let's just do an example really quick. Let's just say we have the prefix M, and we're searching, this product's I is, let's just say that is, I don't know, runner. Okay, well, this runner doesn't contain our prefix M, and if runner doesn't have M, then we know that everything after it also doesn't have M. Let's just call this stars or something. And teach. Okay, so all of these words aren't going to have the prefix if this word no longer has a prefix, because this is an alphabetical order. So that's why we can go ahead and just set end to I there. And remember, the end is exclusive. So yeah, that is the only optimizations I wanted to talk about. Oh, and I need to actually pass an end here. Okay, cool. Let's run this. Make sure it still works. Cool, so that's the optimized version of sorting the products list and then doing a binary search or doing a lower bound binary search. So now let's actually talk about the time complexity. So we can go ahead and let's just do the time complexity, and then we'll do a space one. Or we're doing both at the same time, who knows? So let's start at the top. So Java's arrays.sort. In terms of time, it's n log n, because I believe it's based on some sort of merge sort. In the documentation, that's what it says anyway. And for space, this is, it uses O of n. So this is just Java's. If you're doing this in a different language, then it could be different. But Java's, it creates at most n extra space. Okay, and we don't count this because it's the output. So we don't include the input and output in our space. Let's keep going. So this right here, this little loop, this is O of, we'll just call this search word, the length of the search word, we'll just call that S. And so in Java, strings aren't, they're not like in C where you can just like have an array of characters. So this would actually create a brand new string. So it allocates a space for it, and then it copies over the characters. So this would actually be O. We could just say this is upper bounded by O of S. So this is time. This is both time and space for O of S. And I'll just go ahead and just put time for now. Okay, we'll just delete it. Okay, moving on. So lower bound. Okay, let's go into here. Let's figure out what this is. So we know a binary search is log n, right? I think everyone knows that. So binary search is log n. So let's just go ahead and n in this case is the length of the products. But there's a caveat here, which is why I'm taking a little longer on this method. The strings compare to checks letter by letter. So even though we're running this log n times, what we're doing inside of it is actually, I'm just going to call this, we can call this O of P because this is the prefix. But this is just going to go letter by letter in the prefix and compare it to our products, right? So we could say this is upper bounded by prefix. It's basically the min of the short, the min of whichever string is smaller. We're just going to assume that, to make this simple, that the prefix is smaller than the products. So O of P, and so if we're executing this log n times, that means that this is actually P log n, or P times log n, however you want to write it. I'll just write P log n. And this prefix is actually, well, it's going to eventually be this search word. So I'll get to that. So this lower bound here, let's get rid of these extra comments. We said this is, we'll just copy paste this. This is P log n for the prefix, but this prefix is eventually going to be as long as the entire search word. So we can just go ahead and say that this is upper bounded by S log n. And finally, let's see, we're not done yet. So starts with, or let's see, actually, this is just constant time because this is at most 3 operations. So we could just say this is O of 1, right? Because we only looped through this 3 times here. Okay. And product starts with prefix. Let's see. What is this? This would be O of S again. And let's see, this is just O of 1, then we just return it. Okay, so now let's actually calculate what this entire loop is. So we'll take the big O of this, which is this guy, because S log n is bigger than S, and S log n is bigger than, well, this would actually, so because we're doing S here and this is O of 1, this would just be O of S for the whole thing. Or maybe I'll just be explicit. This makes sense, right? This is, there's OS operations here, and this is constant time, then we just have O of S out here. So anyway, the bigger of, or the maximum of all 3 of these is just this guy right here. So we're going to take this S log n, multiply it by our S operations up here, which just means we have S squared log n. S squared log n is our time complexity for this, and that means the whole thing. Oh, so it's it's this guy plus this guy. So let's just copy paste one of these. So the time that it takes to sort plus our S squared log n. And remember, n is just the length of the products, and S is the length of our search word. So I'm pretty sure that's right. I'm like 99.9% sure. Let's keep going with space. And what is the space of this? So I think it's just bounded by O of n here. Is it O of n? Let's see. Am I missing anything? O of n. Space here is O of s. So I guess we could have. Yeah, so it's actually O of n plus s, because this prefix here takes O of s space, and yeah, I'm sure there's something else in here. Let's see. Is that it? Yeah, I think that's it. The only extra space we created is in here. So it'd be n plus s. So yeah, that's the time complexity and the space complexity. I think that's everything. So yeah, thanks for watching the video, guys. And if you guys want me to do more, you can subscribe. Later.